Well, hi. Our purpose for today is to review for your test, and I just want to remind you of the things that we talked about so far. The quantity that we measured was momentum, or P is for impulse, the Latin word for momentum. And how do we define momentum? Mass times velocity, easy peasy. And it is a vector quantity, as evidenced by its little party vector hat. And the key thing about momentum is that it is created by a force acting over time. And so our impulse momentum theorem is that if you have an object subject to a force, then force times time is equal to the change in its momentum. Just like that. And this was a hidden way of rewriting Newton's second law, because F is equal to ma, which is equal to m times delta v over delta t, and m times delta v is delta p. And if I now clear the fractions by multiplying both sides by delta t, then you have it. Ta-da. All right. So that impulse momentum theorem then led us to discover something wonderful, and that is for isolated systems with no outside forces acting, then wow, that was terrible. Isolated systems, delta P will be 0, which means that P final has to equal P initial. And we call this conservation of momentum. And unlike conservation of energy, where you have to check to see if your forces are conservative, in the case of isolated systems, all forces conserve momentum. And that's a consequence of Newton's third law. Because if you have an isolated system, then when forces act on each other, they act in pairs. And so the action and reaction force create equal but opposite changes in momentum. They cancel out. And our major model for isolated systems was collisions and explosions. And the reason that collisions and explosions can be treated as isolated systems is that the collision happens so fast, and the outside forces, like friction or whatever, are really small, negligible in comparison to the internal forces of collision. We saw that like with a bat acting on a softball, right? In that 3 milliseconds where the bat hits the softball, the force spikes up to like 18,000 newtons. Well, air resistance is negligible compared to that. And so because the outside forces are negligible, therefore, this, for all practical purposes, a collision can be treated as an isolated system in that moment of collision. And so we took our collisions and explosions, and we classified them according to 2 characteristics. First of all, do the objects stick or bounce? If they stick, what type of collision are we dealing with? Totally inelastic, right? And if they are sticking, the consequence is that the 2 objects now become one object with a common final velocity. And that meant that we could use conservation of momentum to solve, and we were done. The second characteristic was, is kinetic energy conserved? And if kinetic energy is conserved, then we call the collision a totally elastic. Here's an interesting question. I have 2 different characteristics, and each one's a yes or no question, right? So technically I should have 4 options. Stick, not conserved, totally inelastic. Not stick, bounce, conserved, totally elastic. How about bounce and energy not conserved? Partially elastic, right? Good. And for these, you would need some additional information. We usually just use conservation of momentum to solve the partially elastic collisions. The fourth possibility, theoretically, could be that the objects stick together and energy is also conserved. I won't do it here, but you can prove that if the objects stick together, then energy can never be conserved. So it turns out that although that's theoretically possible, the equations work out such that it doesn't happen. Okay, so, and one of the things that we like to do, other than find final velocity, was to find the percentage of kinetic energy lost. So that was a common thing. And so one of the computations that we want to be able to handle is percent K lost. And we computed that as delta K over K times 100%.
That's the K initial, right?
Delta K would be...
No, the body K.
Oh, K initial, yeah. Okay. And then more recently, we were taking a look at center of mass computations. And the two things that we really needed to worry about with center of mass were, first of all, what is center of mass? Center of mass is going to be the weighted average of the position of all the objects in your system. So it's going to be the sum of mass times position divided by the sum of masses. And what that does is it takes all the different objects in our position, just averages all of those masses, but it counts each object according to how heavy it is. So the heavier objects get more weight than the average. And then we did a little bit of algebra to determine that the total momentum of the system turned out to be equal to the total mass of the system times the velocity of the center of mass. And what that meant for us is that we were able to treat the entire system as a single object concentrated at its center of mass. So if I have a galaxy, that galaxy contains bazillions of atoms packed into stars and planets and blah, blah, blah. And I don't have to account for the motion of each individual particle. I can just take that whole galaxy and treat it as a single object concentrated at its center. Yeah.
Is there a difference between X center of mass and V center of mass?
Yes, yes. So the velocity of the center of mass
Is the speed of the entire thing?
is the velocity of the entire thing. It's going to be the rate at which the X center of mass changes. And so this enabled us to solve cool problems like the balloon problem and the man and woman pulling each other on frictionless ice problem, and so on and so forth, in which, if I have an isolated system, here we go again, the total momentum of that system will not change. In particular, if my system is stationary at the beginning of the problem, then the center of mass has to remain stationary during the entire problem. That's the whole chapter.
Is that center of mass like a formula? What's the I stand for?
The I is your index of summation, and I omitted it right here. What what you're doing is you are summing up, you're taking all the objects in your system, and you're just numbering them. 1, 2, 3, 4, 5 objects. And I is the variable, called an index variable, that refers to the numbers of the objects. So if I had a system like this, and I want to go through and find the center of mass, then I would start by numbering these guys. It doesn't really matter how I number them. And then I would go through, and for I equals 1, I equals 2, 3, 4, and 5, I would compute mass 1 times x1, mass 2 times x2, etc. And then add them up. So this sum right here can always be written out also as long ways like this. We call this the unrolled form of the sum. We call this the rolled up form of the sum. So you take this whole thing and you roll it up the table. Okay? Good. Well, this time, the floor is open for questions. Yes, sir.
Number 76.
Number 76.
Yes.
Number 76. Okay, let's do it. .192 is the page. Two balls of masses blah 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 suspended. The lighter ball is pulled away to a 60-degree angle with the vertical and released. What is the velocity before impact? What is the velocity after the elastic collision? And what will the maximum height of each ball be after the elastic collision? What a great question. NA is 40, NB is 60. And the whole length is 30 centimeters. Okay. Now, the first question that they ask us is, what will the velocity speed? I think they ask for speed. Ask for velocity. Yeah. And we'll have to give direction to it. Is it this angle right here? What will the velocity be right before impact? So now here I want to think through the process in order to determine what tools I'm going to use. Because if you think about the entire semester, I've actually only given you a few tools. I've given you Newton's laws. I've given you conservation of energy. And I've given you conservation of momentum. How about that? We pretty much have 3 ways to solve problems. Cool. That's kind of freeing because it means that my toolbox really only has to have 3 items in it. And I'm just going to bust out one of those as appropriate. So let's check and see what we want to do. First of all, we recognize that Newton's laws is kind of the hardest way to go about it, so probably don't want to do that. That's going to be our last resort. And in fact, professional physicists think of it as the last resort. First, conservation of energy and momentum. The process that gets me from here to here, right before it hits, what is the force operating in that process? Gravity. Is that no force? There's also tension. Are those forces conservative? Well, gravity is conservative force, I know that. And the tension is always going to be pulling this way while the object goes that way. What's that angle? 90 degrees. So how much work does tension do on this thing? 0. So I don't have to worry about the tension. My only question is gravity a conservative force? Yes. Therefore, I can use conservation of energy to get me from here to here. And I only have to worry about the vertical direction because conservative forces do not care about path. They don't. Doesn't matter if my ball goes this way, or straight down, or loop-de-loop, or whatever. I'm going to have the same amount of energy delivered by gravity as I move from this height to this height. So my hard problem is now reduced to an easy problem. How high is the ball before it falls? Any ideas for finding it? From due east, okay. All right, good. All right, so here's my question. How large is this distance? See what you can figure out. Go. You have to have a couple of key insights. They're not hard insights. You have to have a couple of key insights to answer this question. Imagine you're taking the SAT. They ask you to find this distance.
The ACT last week. Pretty good at that.
Good. Hint, if you're having trouble, look for triangles. And especially right triangles. Ah, great question. What about the problem allows us to assume that the strings are the same length? Yeah, the fact that the balls collide means that the strings are going to be within a centimeter or so of each other. And if they collide head on, then they have to be exactly the same. That was one key insight that I was referring to. And so let's go ahead and put that into the problem. And then, Jayla, have you found a triangle yet? Okay, draw it. Let's see it. Okay. So Jayla's got a right triangle right here. Good. What are the angles in this right triangle? Go ahead and mark the angles. Okay. You mark 2 of the angles. Okay, you could accomplish. What do you tell? Okay, 2 ways to find that angle then. First is, because you have a right triangle here, these 2 angles must add up to 90 degrees, right? And also because you have a right angle here, these two angles must add up to 90. What's that? Does 40 and 60
Oh,
add
no,
up?
I was talking about the one that says the 70, the 30.
Oh, the 30 centimeters is not an angle, that's just a line,
Okay.
right? What does this angle have to be? Does 40 plus 60 add up to 90?
Oh,
Has to be 30, right. This angle has to be 30 degrees, and that means this angle also has to be 60 degrees. And we'll get confirmation of this because we have parallel lines cut by a transversal. Who knew all that geometry stuff? Actually, we do. Yes.
Earlier we said that the angle where the law MA is, we call that a right angle because,
Which angle are we talking about here?
where your fingers, right there.
Like that?
No,
There.
earlier we.
Oh, like this.
This.
Yeah, that's true also. It's not very helpful to us.
Yeah.
But the angle between the path and the strain will always be 90 degrees. Yeah. So that's a true fact. It's not very useful to us in this problem, except to observe that the tension will not do work. Once we've got that, now the game is won because this is 30 centimeters. That means this guy right here has to be 30 times the sine of 30 degrees, or 15 centimeters. And if this is 15 centimeters, then that means that this distance is whatever is left over, which is 15 centimeters. And there you go. Okay, that was the hard question. Please notice that this kind of diagram with a pendulum like this is a very common scenario, and we want to be able to take it apart. And the key was to identify that if this is an angle theta right here, this guy is 90 minus theta, and so this guy right here will be equal to the length times the sine of 90 minus theta, or in other words, the length times the cosine of theta. Yes?
How did you get
Because in my right triangle, this side, let's call it y, is opposite to the 30-degree angle, and therefore y over the hypotenuse is equal to sine of 30 degrees. Opposite sides are always sine sides, right? Adjacent sides are cosine sides. Okay, so what we've done then is we've seen that for part A, our work would look like this. We would say, we would do the preliminary diagram work over here, and then we would say that total energy is conserved. And the total energy at the beginning is going to be 0 kinetic plus mg times 15 centimeters. I'm going to write that 15 centimeters as 1.5 meters. Equals 1/2 mv squared plus now nothing. Now I'm implying that I had a 0 point here, and my 0 point is right at the bottom. Yes. Potential energy. Notice that the mass of the ball cancels out of this equation, so it doesn't matter that it's a 40 gram ball. And so my velocity turns out to be 1.7 meters per second. Excuse me, my speed. Here we go again. They asked for velocity. What are we lacking? Direction. Which direction is it going to be? Is it gonna be down and to the right? Right as it hits?
No, it'll be very.
It'll be directly to the right. So that's the difference, Grant, between average and instantaneous. The average velocity from here to here is down and to the right. The instantaneous, right at this point, is directly to the right.
So we put 1.7 angle 0 meters, right?
Yes. Or you could write it like that, or you could write it like that. So many ways to write vectors. I would even take 1.7 meters per second that way. Really would. In the larger world of calculus and such, direction is considered to be a vector with length 1 pointing in whatever way it needs to go. So this is a perfectly acceptable direction. What you got? Problem?
I got a different answer.
We got a different answer. Did we screw up somewhere?
I got one.
Same computation, but different result. Did you multiply this by half instead of 2? What answer did you get? Radical. Did you use 1.5 meters for the height?
No, I didn't. I'll figure it out.
Okay, you'll figure it out. All right, fair enough. All right, now part B. In part B, they ask,
Does elastic is each ball?
we call it the elastic collision. Oh, they had to make it an elastic collision. By the way, what common toy is the model for elastic collisions? The little, yeah, it's called a Newton's cradle, right? You've seen it all with the 4 balls, right? And how do I know it's got an elastic collision? Because if I let it go, what does it do? It keeps going, just like that, for a really, 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 really long time. The reason for that is that in each collision, energy is essentially conserved. And so, if you think about it, after it goes through one cycle, boom, boom, it goes back to its original state, which means it's going to cycle forever. Now, is energy completely conserved? No, it's about 99% conserved. And the reason you know it's not completely conserved is that eventually it winds down. Okay, so we have a totally elastic collision, and at that point, our 2 tools for totally elastic collision come into play: conservation of momentum and conservation of kinetic energy. So here we go. We just write P0 equals P final, and so that means that mass 1 is 40. Notice that my units are grams, but that's okay. 40 times 1.7 meters per second, plus 60 times 0 has to equal 40 times, let's call it VA, and 60 times VB. And we recognize that VA and VB are going to be vector quantities. They're going to have a direction, but that's not going to show up in our equation. So even though I suspect that VA is probably negative after the collision, I'm not going to write a minus sign there. I'm going to let the VA naturally be a negative number. Yeah. So there's that. And then I'm going to set up kinetic energy is conserved, just like so. Notice that I don't really know how this is all going to work out just yet, but I can still do the conservation of momentum and energy just like that. So But because it was a totally elastic collision, my Pavlovian response kicked in, and I just wrote the equations for momentum and energy on that. Then having done that, then I'm going to go through and I'll trouble myself with how do they work out. One thing I observed is that all of my masses have a common factor of 20. Did you observe that? So it makes sense that I would take and simplify these equations by dividing through by 20 here, and that gives me 2 times 1.7 equals 2VA plus 3VB, and that's a lot less scary. And likewise down here, I'm going to multiply through by 2 and divide by 20, so that gives me 2 times 1.7 squared equals 2 times VA squared plus 3 times VB squared. And that's a lot less scary as well. So I have these 2 equations that I need to solve as a system. And now what are my solution options? Yep. Substitution and elimination. I've tried to guide you that substitution is usually the way to go for these. You can also try elimination, it's fun. Once I've got the substituted equations, what are my solution options for that? Graphing or the A word? Algebra, right. Exactly. It turns out that
Conversation got late,
what's that?
I joined into that conversation kind of late, and so I just hear the A word, and
Yeah, that's right. So, so the question is, which one is better? I'm not sure till I substitute. So let me do that. If I take the top equation, 3.4 equals 2VA plus 3VB, and I'll pick a variable to solve for. I like solving for VA. Then that gives me 1.7 minus 1.5 VB is equal to VA. Check the algebra on that. Subtract 2. And now substituting into here, I get this equation right here. It's not obvious, but it turns out that if you were to simplify this, then you get a factorable equation. But since that's not obvious, the decimals obscure that fact. And then probably a calculator solution would be recommended. Go ahead and solve that equation on calculator. You'll get 2 solutions corresponding to the before and after situations.
he's confused on the triangle solution.
7 times 6. Oh my gosh.
You should be able to show some.
Well, you're overcomplicated.
I'm sorry, let me draw 3 triangles first.
It actually is easier. And you only use drawing.
Okay. So you're trying to use. Okay, that's the one because your angle. If you think of this as a vector, right? And the tail of the vector, the head of the vector, and the tail of the vector. So well, you measure the angle of the vector from its tail, not its head. This is the. This is not tail. Yeah. So you were in the wrong sum. You were in the wrong sum. Yes. Ah, okay. So that can work. Although there is a dividing by 2 that needs to happen first. Right? So you, right, yeah, so actually. Like that. Because you divide 3 by 2. That'll get you there. I like substituting into, solving the linear equation and substituting into the quadratic. You solve the quadratic and then you're going to substitute into the linear. It'll work,
Oh,
but
yeah,
it's more
it
of a
won't
pain.
work.
Yeah. Okay, and when you do solve, oh, do I want to do this by hand?
For the graph. Do you want the answers?
Yeah, what do you got?
BD equals 1.36, comma 0. Like what you do.
Or VB equals 0. Yeah. I like the word or, because that makes it clear what's going on.
What you see the graph.
Okay. And we already know what the VA is that corresponds to that. If that's interesting. VB is 1.36.
Yeah.
Okay.
And the other VA
Would be 0.4.
0.34. Or 0.34.
Oh, because minus 1. Okay, so it's actually negative 0.34. Okay, yes. Yes. That makes total sense. Yep, because VA is a smaller object, the MA is a lower mass than MB. It is necessarily the case that MA has to bounce off and go back the other way. If it had more mass, then it would carry through. Yes?
I didn't get those values.
You didn't get those values?
Yeah. I
Basically,
got, is minus a parabola, so I got the same thing for both intersections.
let's see what we can have. Yeah, you got 2 intersection points, 1, 2.
Yeah.
So what do you mean when you say you got the same thing?
I got, like, at those intersection points, I got y equals 5.
Yes, the y's are not what you're looking for. The x's are what you're looking for. Because the x's, if you look at this equation right here, what you did was you said y1 equals this, y2 equals this, right? So the y value is just going to tell you this quantity right here. The x value is going to tell you VB because you represented VB as x in your calculator. Does that make sense? You got to keep track of what your data is. And the last question is, what will be the maximum height of each ball after the elastic collision? So here again, we have to do some conservation of energy. For ball A, we're going to set energy final equals energy initial. Cancel, cancel. Notice that if I do this symbolically, then I actually get a formula that I can plug into for each ball, right? This is not what I want. I want the height equation. Same thing. If I do it symbolically, I can get an equation for each ball and just plug in directly. So for ball A, I get 0.34 squared over 2 times 10, which is going to be small. gonna be 0.00578 meters. Huh, let's get a sense of what that is by writing it in its original units, 0.5 centimeters, 0.58 centimeters. 0.58 centimeters is gonna be like this. So this thing is gonna come down, and it's just gonna barely rebound a little bit. Meanwhile, how about ball B, same equation, different values. But ball B is going to rebound to a height of 9.2 centimeters. Now here's the crazy thing. I'm not going to prove that at this time, but I think physically it will at least be plausible to you that when these two go up, they're not going up to the same height, right? One's going barely like this, and the other one's going up like this. Well, 9 centimeters, so 9 centimeters. The other one goes up like this. When they come back down, they will actually meet at the same place. And when they meet at the same place, shockingly, this ball will knock this guy right back up to the original height of 15 centimeters, and will stop. And then it'll come back and oscillate just like that, just like that, just like that, and we'll keep on going. What's fascinating is that the two of them meet in the same place. Why? If this guy only has 0.58 centimeters to travel, and this guy has 9.2, how is that possible? Well, the answer is this guy's going to be moving a lot faster. So he's going to cover this ground in the same amount of time that this guy covers just this little bit.
So simply would that happen now?
Yes.
Even with it being, you said it was a bigger ball.
So what will happen is on the first hit, boom, and rebound. On the second hit, boom, and rebound.
So this one goes in, it's just a lot less.
Actually, it moves 0.
Okay.
Right.
So it's that Newton thing, right?
It's the Newton thing. Right. Exactly. All right. So this was a great, great problem because it illustrated both conservation of energy, potential and kinetic, when that's appropriate, and also elastic collisions. I highly recommend taking a second whack at this problem and talking yourself through it.
This is a lot easier than the way I was trying to solve it, because I automatically went to forces and Newton.
Yeah, because you learn it first, you think, oh, this is the easiest tool. But actually, it's the other way around. You learn it first because it lays the foundation for stuff that's more powerful. Think about it like this. If Newton's laws were the easiest way to go, we would stop there.
I did think about it last year.
Okay, well, that is it. I hope you guys found this profitable,
Yes.
and we'll see you tomorrow.
Still confused about